Welcome back to the next lecture in our module 2, mathematical modeling. Let's have a recap of what we had done so far in this module. We started off with statement of conservation laws, then we had a look at notation and mathematical preliminaries. In past 3 lectures we had focused on the derivation of governing equation of fluid flow, and today in the same series we will focus on derivation of energy equation and scalar transport equation. And thereafter we are going to start off with mathematical classification and boundary condition for the flow problem in the next lecture. Let's have a recap of what we did in the last lecture. We started off with a discussion on constitutive relation for a Newtonian fluid for which stress and strain rate tensor are linearly related, and based on that simplified relation we obtained our famous Navier-Stokes equations. We also derived simplified forms for Navier-Stokes equations for specialized cases, for instance incompressible flows, which gives us a much simpler equation, and we had a look at the cases for inviscid flow, which gives us the celebrated Euler's equation, and we looked at one specialized case which we call creeping flow equation. In today's lecture, that is the 6th lecture in this series, we will focus on energy equation and scalar transport equation. This would be our outline. We will start off with first law of thermodynamics, which is the basic law for energy conservation, and we would have a look at what we mean by flow work. Then based on the first law we would obtain integral and differential forms of energy equation. Then from this equation we would derive a specific equation which we call thermal energy equation, and in the end we would have a look at equation for a generalized scalar transport. So now let us start off with the first law of thermodynamics, which is the basic equation for energy conservation. What does this law say? Let us recall back what we learned in our thermodynamics class. It says the time rate of increase of the total energy stored in the system, this is equal to net rate of energy equation by heat transfer from the surroundings plus net rate of energy addition by work done on the system. Let us use our usual symbols. We use capital E to indicate the total stored energy of the system. So dE by dt, this represents the time rate of change, or rather the rate of increase of the stored energy in the system. This is equal to del Q by del T, where Q is heat transfer. We have used symbol delta to indicate that Q is not a state function, it depends on the path. So that is why we would use these inadject differentials on the right hand side. So del Q by del T, this gives us the net rate of energy addition by heat transfer, and then we have followed the typical convention used in thermodynamics, that is to say that work done is considered as positive if it is done by the system on the surroundings and negative vice versa. So here we are looking at the work done on the system, that's the reason we have introduced negative sign here. So del Q by del T minus del W by del T. We would look at each of these terms separately, and thereafter we would obtain our integral form of energy equation. So now let us have a detailed look at each term. We had total stored energy of the system, now in those total energy capital E, we have got to account for what we call internal energy, in thermodynamics we normally use symbol capital U, plus kinetic energy plus potential energy. PE. Now if you remember, in potential energy arises because of the presence of a field, of some force field in which our system is embedded. So, this potential energy is essentially the work done by the body force on the system. Okay, this being the case, what we will do is we would absorb or transfer this term, or rather account for this term for potential energy in the work done term, this is del W by delta T. So, we do not need to put it in as a part of E. So, thus our capital E would consist of only two terms, that is our internal energy plus kinetic energy. Now, internal energy per unit mass we will choose a slightly different symbol, let us call it small e to denote the internal energy per unit mass, because usual thermodynamic symbol small u we use for velocity component in x direction. So, that's why let us choose a different symbol. Kinetic energy per unit mass, this would be given by half square of our velocity magnitude. So, thus our specific total energy let us use a symbol eta for it. Eta is equal to E plus half of modulus of V squared. Let us note the relation between capital E, that is total energy, and eta. That is very simple. Capital energy is basically integral over the whole of our domain. So, that is rho eta dV over domain omega. So, now let us invoke Reynolds transport theorem. So, from Reynolds transport theorem, our dE by dt, which occurs in the first law statement, dE by dt for our control mass system, this would be, the first one would be time derivative, or this temporal variation of the stored energy in the system, this is rho eta dV, and plus the flux of this energy across the control surfaces. So, we have got rho eta V dot dA. So, this one expression, which is rather an expansion of the left hand side of our first law of thermodynamics, that is dE by dt term in terms of the quantities related to the control volume. Next, we will have a detailed look at two other terms on the right hand side. So, on the right hand side we had one term, now we had heat transfer. Now, there are two principal components of heat transfer for our fluid body omega. There would be some amount of heat which is generated internally, let us call this volumetric heat generation at Qg. So, heat transfer is caused by two mechanisms. Number one is our internal heat generation. Now, this internal heat generation could be due to chemical reaction, or it could be, let us say, a nuclear reaction, or maybe an embedded heater throughout the volume. And the second term would be the heat transfer from surroundings So, can we find out the total amount of each of these terms? So, if Qg is our volumetric heat generation, rate, then its contribution is total contribution we can express in terms of a volume integral. So, let us use a symbol delta Q by delta T, the subscript G, which denotes internal heat generation. So, this is integral of Qg over our volume Now, how do we obtain the next term, that is the heat transfer from the surroundings? Let us look at one small boundary here, and if the Q were the heat flux, normally we say that Q would be directed outside, this is heat flux vector across an area element dA. So, Q dot dA, that will give us the energy or the heat which is leaving our control volume. But we are interested in finding out how much heat is being transferred from the surroundings to the system or to the control volume. So, heat transfer through control surface let us call it del Q by del T of S. We have to put a negative sign because Q dot dA, our integral surface integral of that term, will give us the amount of heat which is going out per unit time, and what we are interested in finding out how much energy which is being transferred inside the system. So, this would be Q dot dA. So, if we combine these two terms, we can find out the net rate of heat transfer into this control volume, or rather the system which instantaneously occupies your control volume, occupying the control volume. So, del Q over del T, this we can express as a first term would be a volume integral Qg, or if you want to make use of the rate process involved, we can put Qg dot. So, Qg dot d omega minus Q dot dA. And nature of these two terms is very clear. The first term, this Qg dot d omega, this is due to internal heat sources, and this later term, this surface integral, this tells us the diffusion of heat through control surface. So, now we have obtained the mathematical form for the rate of energy transfer due to heat. Next, we need to have a look at the rate of work done by the surroundings on the system. So, work done by the surroundings on the system. So, if you can go back to your mechanics, we know that rate of work done can be expressed in terms of rate of work done is dot product of velocity with force vector. So, now in our case we will in general have two set of forces. We have got body forces and surface forces. So, let us treat them separately and find out what is the rate of work done by each component. So, the forces involved are a body force and surface force. So, let us take the first case, that is a rate of work done by body forces. Let us take a small differential element. So, rho into d v, that will give us the mass of this small element. It has got the velocity v and the body force acting on it per unit mass is b. So, what is total body force on this small differential element? This force dFb, that is b times rho dV. So, differential rate of work done delta Wb dot, this would be V dot B rho dV. So, to find out the total rate of work done by the body forces, let us call that as del W B over del T. This would be negative of volume integral over the control volume rho V dot B dV. Okay, the next we have to look at what is the rate of work done by surface forces. So, rate of work done by surface forces. So, let us consider a small area element on the surface dA. So, how do we obtain the surface force on it? dFs, that we can obtain by taking the dot product of the stress tensor with our area element. So, this gives us the surface force acting on a differential area element dA. So, now rate of work done due to surface forces, that would be V dot dfs, which is equal to V dot tau dot Ta. So now we can easily find out total work done by the surface forces. So this rate of work done by surface forces, let us call it as delta Ws by delta T minus V dot tau dot dA. Please remember, we have been putting this negative sign to take care of the sign convention using thermodynamics. Okay. So thus net rate of work done by surroundings on our system is minus delta W over delta T. That will be some of the two integral relations which we derived earlier. The first one which corresponds to our work done by body forces, and the second one which corresponds to the work done by surface forces. So combine these two together, so we get rho V dot B dV plus the area integral V dot tau dot dA. So now we have got detailed expressions for all the terms, the three terms which we started off in our first law of thermodynamics. We have obtained the detailed expression for dE by dt. We obtained a quantitative expression for delta Q by delta T, that is heat transfer into the system from surroundings, and we have also obtained a quantitative expression for the work done by the surroundings on the system. Let us combine all these together, and if you do that, this is what we get. We get the integral form of energy equation. So on the left hand side we have got del rho by del T rho eta d omega. So this is the time rate of change of the stored energy into the control volume, plus second term gives us the flux rho eta v dA, the flux of energy which is going out from this control volume, and on the right hand side the first two terms, these account for the heat transfer Q d omega, is volumetric heat generation, and second one is heat diffusion Q dot d omega, plus the next term is V tau dot dA. This term we also refer to as flow work, plus we have got to include here the work done by body forces, which is missing in this expression at the moment. So a complete expression would be this is what we had, dE by dt is equal to delta Q by delta T minus delta W over delta T. dE by dt we had obtained its expanded form using Reynolds transport theorem. This is del by del T of rho eta dV plus the surface integral, which gives us the rate of efflux of energy from the system, rho eta V dot dA. Now this is equal to, first let us put that expanded form for del Q by del T. Del Q by del T contains, first one is our heat generation term, Qg d omega So, volumetric integral of that minus q dot dA. So, this q dot dA, that represents the heat which comes in. Q is the heat efflux vector. So, negative sign here, that gives us that how much heat is being transferred into this control volume from the surroundings. Plus now work done term, work done by the body forces, rho v dot b d omega, and the last one is work done by the surface forces, v dot tau dot dA. So, this is our integral form for energy equation. For total energy. Now, sometimes we might be interested in only the transport of thermal energy. So, in that case what we need to do is take out the mechanical component, which can be easily done if we multiply or we take dot product with V of our Cauchy equation. So, that will give us the rate of mechanical energy transport, subtract that from our integral form of total energy, and we will get an integral form for thermal energy. But for the time being we will stop here as far as the integral forms are concerned. Next we would like to derive a differential form for energy equation. So, how do we obtain the differential form for energy equation? Once again we will follow the same approach which we had followed earlier in the derivation of different differential forms like Cauchy equation and momentum equation. First we need to transform all the terms which we had in integral equation into corresponding volume integrals. So, now let us transform each one of them separately. The first one, this del by del T of rho eta dV, this can be written as volume integral over omega of del rho eta by del T dV for fixed mass. So, for fixed mass what we can do is we can assume that look, time derivative or the temporal derivative and the integration they can be easily interchanged. Next let us use Gauss divergence theorem to transform all the surface integrals which we had into volume integrals. So, using Gauss divergence theorem, let us see, let us have a look at each one of the surface integrals. This is the first surface integral on the left hand side. So, let us see what do we get for it. Rho eta v dot dA, this will be given by the volume integral of what? Divergence of whatever terms which we have got before the dot operator, that is rho eta into V. So, rho eta V d omega. So, we have now transformed the surface integral which we had on the left hand side into a volume integral. What will happen next? We have got two surface integrals on the RHS, that is q dot dA and v dot tau dot dA. Now, let us transform these ones also into respective volume integrals. So, q dot dA, this simply becomes divergence of q d omega, and our last surface integral, that is our v dot tau dot dA, once again, while using the divergence theorem, all that we need to note down is terms which occur before dot dA, we have to take divergence of those terms. So that this will give us divergence of V dot tau d omega. So now we have got the corresponding forms or volume integral forms for all the surface integral, and we will collect all the terms on left hand side. So let us substitute and rearrange the integral form of energy equation. So what we will get? We will get a very big integrand inside, or volume integral omega. Let us put a big bracket. So the first term is del of rho eta by del t. The second term is divergence of rho eta into a velocity vector. Then now the terms which have come from the right hand side. So first term will give us minus qg dot. Next we will get divergence of q and minus rho v dot b, that is contribution for body force, and the last term is on this integrand would be divergence of v dot tau. Let us close our big bracket d omega, which is equal to 0. So we apply the same argument. Here we have got an integral which is 0 for an arbitrary control volume omega. So we can argue that integrand would be 0 for an arbitrary volume, control volume, if and only if the integrand is 0 everywhere. Integrand is 0 everywhere. So thus what we get? Let us set our integrand to 0. So we get del of rho eta by del t plus divergence of rho eta v minus qg dot plus divergence of q minus rho v dot b, sorry, that is minus divergence of v dot tau, this is equal to 0. Rearrange so that we have terms in specific energy on the left hand side and remaining terms on the right hand side. So del of rho eta over del t plus divergence of rho eta v is equal to qg dot minus divergence of q plus rho v dot b plus divergence of v dot tau. So this gives us the differential form of energy equation, and this is what we have summarized here. So, differential form of energy equation in conservative form, del rho eta by del T plus divergence of rho eta V, and this term missing in this equation PPT here, that body force term. We have obtained the differential form for total energy equation. Now, if you want to obtain the equation for thermal energy, we simply need to subtract the contribution of mechanical energy. On this later part, this could be obtained by taking dot product with V with or velocity vector of momentum equation. Okay. Now, the final equation is in terms of our internal energy E, del of rho E by del T plus divergence of rho E V. This is equal to our heat generation term Q dot G minus divergence of Q plus gradient of V double dot tau. This last term has been obtained from some algebraic manipulations from the last term in our total energy equation, and its expanded form is del V dot tau. This is basically del Vj over del xi tau ij, where usual summation conventions apply to give us a scalar term. So, this del V double dot tau, del V, that is a gradient of velocity vector which is a second order tensor, tau is a stress tensor which is again a second order tensor. So, we have to take doubly contracted product of these two tensors to obtain the scalar contribution, okay. And this term represents the work done by pressure as well as viscous dissipation. Now, let us note that if we are dealing with low speed flows, which are very common for the incompressible flows in particular, the contribution of the viscous dissipation would be very small. The viscous dissipation is important only for high speed compressible flows. So, for low speed flows we can simply drop this term off and combine the contribution coming from pressure into a right hand side in terms of enthalpy. So, for low speed flows viscous dissipation is negligible. Contribution from pressure work can be combined with internal energy and this gives us the resulting equation for such flows, that is low speed flows, resulting energy equation becomes rho Cp d of capital T, where capital T represents the temperature, and this capital D by dt, this gives us material derivative. This is equal to q dot g minus divergence of q. So, this is the thermal energy equation for low speed flows. For low speed flows, here capital T stands for temperature and Cp is the specific enthalpy at constant pressure, sorry, specific heat at constant pressure. So, Cp stands for a specific heat at constant pressure. Now, for some substances, specifically for heat transfer or in thermal energy transfer in solids, we can invoke Fourier's law. So, for the substances obeying Fourier's law, we have got a very special relationship between heat flux q and the gradient of temperature. So, the heat flux vector is given by minus of k into gradient of T, where k is here, this k is thermal conductivity. For an anisotropic substance, this k would have 9 components, it will be a second order tensor, but for simple isotropic medium it would become a scalar quantity. So, now if you substitute the Fourier's equation in the thermal energy equation which we have obtained earlier, so then we get it in the simplified form rho Cp d of capital T by dt, this is equal to qg dot plus divergence of k times gradient of T. So, this is form of thermal energy equation for substances which obey the Fourier's law. So, in this lecture we stop here. In the next lecture we will have a look at conservation of scalar quantities. We would obtain a transport equation for a generalized scalar transport, and then we will have a look at mathematical classification and the boundary conditions which we require for the flow problem.